Hey there guys, welcome to Unit 9 Notes E. In this last set of notes for thermodynamics, we're going to put everything together and look at spontaneity, or whether a reaction will spontaneously occur on its own. Does it have enough energy to do that? So all about spontaneity today. The first factor I want to look at is called entropy. Entropy is essentially a measure of how unorganized or chaotic a system is. We can determine entropy similarly to the way that we determined the enthalpy of formation. When we looked at the enthalpy of formation of reactants and products, we could get the enthalpy of the total reaction. You can do the same thing with the entropy of the product and reactants, and that will help you determine the entropy of the total reaction. Again, you would look it up on the chart, just being careful that you're in the delta S column. So S is the symbol for entropy. This is going to allow us to figure out if the chaos in the system is increasing or decreasing. There's some other more qualitative ways to tell as well. The idea with entropy is it is natural to be more chaotic. If things are becoming more chaotic, that would be a positive entropy, as the entropy is increasing in the system. However, if the disorganization is decreasing, meaning you're making it more orderly, that would require an input of energy. That would decrease the entropy with a negative S. So chaos is our entropy, where organization would be low entropy. So let's just take an example of a solid substance versus a liquid substance. Which one seems more chaotic? The liquid substance. Those particles are moving around each other and moving and bumping, whereas if you looked at a close-up picture of a solid particle, that looks very organized. The particles are sitting next to each other in rows and columns. So as you increase the motion, you increase the chaos. So solids would be the least entropic or chaotic, all the way up to gases being the most chaotic. Solutions would fall somewhere in between liquids and gases. They are in the same phase. Usually the solutions would be in an aqueous phase, so they would be similar to liquids. However, it is more chaotic to have a mixture than it is to have a pure substance. The organization of having something only with its own particles is preferable to having the mixture. So entropy would increase if you mix together things. It is more chaotic. Anything that's breaking down, you're going to increase the chaos. So this also applies to kind of looking at coefficients. When you're looking at gas particles, if they're separating into more particles, that again would be more chaotic. So you can compare the moles of the reactants to the moles of products to see if you're increasing the chaos. Phase would go first. You want to look at the phase first, but given that there's, say, for example, both gases, if you looked at the number of moles, you could then kind of infer the type of chaos. Is it increasing or decreasing? So the reason I wanted to go over entropy first, because we've already spent a whole lot of time on enthalpy, and as it turns out, those two things together are going to determine whether the reaction is spontaneous. So it's enthalpy and entropy, delta H and your S, that are going to dictate the spontaneity of the reaction, or whether that reaction will automatically occur on its own, whether it's going to occur at normal conditions. Just because something is favorable heat-wise doesn't mean that same thing is favorable chaos-wise, and vice versa. Now, of course, if it's favorable both ways, that reaction will definitely happen. And if it's unfavorable both ways, that reaction will never happen. We're also going to look at an interplay, where if one thing's favorable and one thing's not, which one wins? So the kind of overall category of what makes something spontaneous is known as Gibbs free energy. We're going to need to calculate the Gibbs free energy in order to determine if the balance of entropy and enthalpy is going to allow that reaction to proceed. Which condition is going to dominate? So the formula for Gibbs free energy, variable being G, is that you're going to do delta G, set that equal to change in enthalpy minus the temperature times your entropy. You've got to be really, really, really careful about your units here. The delta G on the table is going to come as kilojoules, and your enthalpy will also be kilojoules. But entropy is typically measured in joules per Kelvin. Also notice that we've been using degrees Celsius this entire unit. All of thermodynamics, we keep talking about degrees Celsius, and it's been fine. But in this formula, we have to make sure that we are in Kelvin, we want to look at these variables as they relate to the absolute temperature. So we have to be in Kelvin. That's also going to allow my units to cancel with the entropy given number, and we're going to need to convert my number in joules into kilojoules in order to get the units to match up energy-wise. So watch your units, but other than that, it's just a algebraic plug-and-play type of problem. But what does it really tell us? Well, the idea is to be able to determine delta G and find its sign. If it is a positive delta G, that would represent the need for an input of energy. That means the given enthalpy and entropy of the situation is not enough to allow the reaction to proceed on its own. You would have to input energy in some way. For example, inputting an electrical energy, which would therefore cost you money. So the idea is typically we want reactions to be spontaneous. We want to design chemical reactions that are going to automatically give us the products without costing us money. So we want a negative delta G in order for the reaction to occur on its own without needing that extra input of energy. So you can tell by your delta G whether that reaction is spontaneous or not. Negative, yes. Positive, no. So let's look at how the different enthalpy and entropies play together, this interplay of the system. So the formula, as we talked about, was delta G equals delta H minus T delta S. And the first thing that I want to point out as we start talking about signs is that the temperature had to be in Kelvin, and that means it can't be negative because the lowest temperature in Kelvin is just 0. There is no negative Kelvin. So I don't have to worry about the sign for the temperature. I'm only focusing on the sign for the H and the S. So if delta H is negative, meaning it's exothermic, delta S is positive, meaning I'm increasing the entropy. Those would both be good things for the reaction. We would want energy to be available to facilitate the reaction. We would want chaos to be there, so the particles are bumping into each other and facilitating the reaction. So both of these things are good. So if I have this negative delta H and a positive delta S, what does that mean for my sign of delta G? Negative enthalpy, meaning exothermic, and the positive delta S, showing I'm increasing my entropy. So the component for the exothermic would be negative, and then minus, temperature has to be positive, and if I have the positive S, this entire component would be negative as well. So if I add up two negative components, I am absolutely getting a negative answer, which is good. A negative delta G will always be spontaneous. And if I have something that's exothermic with an increased entropy, it is impossible to get a positive delta G. So it's always going to be spontaneous. Well, let's go all the way down to the bottom where it's never spontaneous. A positive enthalpy would be an endothermic reaction, and a negative entropy would mean I'm decreasing the chaos. That's unnatural, right? Think second law of thermodynamics. So what does that look like for my formula if I use those signs? So we've got delta G equals delta H minus T delta S again. And the enthalpy would be positive. So this component would be positive, referring to the heat energy. And then if I have a negative S, well, what does minus a negative do? It's going to make that component positive as well. And so when I add two positive components, I absolutely am going to get a positive delta G. Positive delta G is not spontaneous. So if I have an endothermic reaction that is becoming more organized, decreasing the entropy, that will never happen on its own. That's absolutely going to require an input of energy. Now let's look at what's in between. So let's look at the negative, this one. The negative delta H would represent an exothermic, which is a good thing. Whereas if I'm decreasing my S, this decreased entropy, that is a bad thing. So what does that do for my signs on the delta G formula? delta G equals delta H minus T delta S. And if I have the negative delta H, this exothermic thing would be negative, which is good. But if I also have the negative S, since it's minus the negative, that would make my ending component there positive. So if you add a negative component and a positive component, the sign will depend on which one is bigger. So if I want a negative G, I want the enthalpy component to win. I want that to be bigger, which means that I need to minimize the entropy component. In order to minimize that, I need a low temperature. Last option, looking at positive delta H and positive delta S. Delta G equals delta H minus T delta S. So requiring an input of enthalpy, being endothermic is not favorable. That would be bad. But then having an increase of entropy is good. Increasing my chaos is going to help facilitate the reaction. So the fact that that is good means I'm going to have a positive delta S, whereas my endothermic component made the delta H positive. So if my enthalpy component is positive, but minus the positive number leaves my entropy component negative, the only way to get the negative delta G is to make this the winning component. We want a higher entropy so that it will beat out that bad enthalpy. So what I want to do is maximize my temperature at a higher temperature. So if both components are favorable, it's always going to happen. If both components are unfavorable, never going to happen. When one is good and one is bad, you have to consider which one's going to give you the negative G. If it's the enthalpy that's favorable, you want to lower the temperature to minimize the effect of the entropy, whereas if the entropy is good, you want to increase the temperature, so that's the winning component. And that's the only way we can tell whether it will be spontaneous if we have one favorable and one unfavorable. So it's all about the signs. Oh yeah, the red marker is not a good marker, but I really wanted to show it being bad, so give me just a second. All right. Last thing that we want to do is look at the calculation itself. So here's our first example of how to calculate delta G. So it's giving us the enthalpy, which is negative. Is that good or bad? Do we want a negative delta H? That would mean it's exothermic, which is a good thing. Then we look at our entropy. It is positive. Do we want an increase in entropy? Well, yeah, that's good too. That follows our second law of thermodynamics, an increased entropy. So both of these things being favorable tell me that this reaction should happen. And it's a good thing to look at that in the beginning so you can kind of check your signs as you go. Let's actually practice using the formula though, using that delta G equals the change in enthalpy minus the temperature times the delta S. The catch is we have joules in one component and kilojoules in another component. Delta G is typically measured in kilojoules, so I'm going to convert my joules to kilojoules first. So that's going to be 137.55 joules per Kelvin. And if I want kilojoules, then I'm going to make that number smaller by 3. It basically is dividing by 1,000. And so that's going to become 0.13755 kilojoules per Kelvin. The other thing that I want to convert is the temperature. Now it gives that we're at standard temperature of 25 degrees Celsius, but we don't want to use degrees Celsius. We want to convert this to Kelvin by adding 273. So that would be 298 Kelvin for the standard temperature in Kelvin. Once I handle the unit conversions, now I can plug them into the formula. So let's see what that looks like. There we go. So we got our kilojoules we plugged in for delta H, the Kelvin temperature here, and then kilojoules for our entropy. Now we want to just be real careful of our order of operations, solve for delta G, and we get a negative 326.4 kilojoules. Was it supposed to be negative? Well, remember, both of these things were favorable, and so we should be getting the negative delta G. You always want to consider whether the favorable things led to what you were expecting, which is this, yes, a spontaneous reaction. Because both the entropy and the enthalpy were favorable. We want a negative enthalpy, we want a positive entropy. And if you have both of those conditions, you're driving the reaction forward twofold. Both of those things are helping the reaction happen, and so it's definitely going to happen. Let's try one more. In this question, we're being asked to determine if it is spontaneous. So there's a catch here, and they do usually give you a hint on these types of questions. All we know is that we want a negative delta G, so it needs to be not 0, but a little bit less than 0. So standard kind of protocol for what's negative enough is just a negative 0.1. So if we're looking for a negative 0.1 kilojoules, that's going to tell me if I get there, then I have this positive, not positive, then I have the negative delta G, and therefore I will have this spontaneous reaction. That's what I was trying to say. So we have, again, the problem with kilojoules versus joules. And we want the delta G in kilojoules, so I need to convert my 24.3 joules to kilojoules, which means moving the decimal back 3 places. So this is 0.0243 kilojoules per Kelvin. Now I want to solve for the temperature. Now the question specifically says that it wants the temperature in degrees Celsius. The delta G formula is designed for Kelvin, and notice I'm going to be using Kelvin here. So that's going to require you to use that 273 to convert the Kelvin back to degrees Celsius. So first let's go ahead and plug into the formula. Delta G, using that slightly negative number, my delta H, which we don't have to do anything to, that's already in kilojoules, minus T, which is automatically going to be in Kelvin, times the delta S, which we've converted to kilojoules here. So when we solve, automatically getting it in Kelvin, since our Kelvin didn't cancel, we get 5,950 Kelvin. But the question asked for it in degrees Celsius, so we know that we're going to have to add 273 degrees Celsius, or I'm sorry, subtract 273 degrees Celsius. To go from Celsius to Kelvin, you add. So from Kelvin to Celsius, you would subtract. And so we would get our final answer as 5,677 degrees Celsius. That means that's the temperature that would be necessary in order to make the reaction happen. Let's take a little step back here and think about what things were favorable and what things weren't. We have a positive entropy. We want an increase in entropy. So that is positive, that is favorable. However, we want a negative delta H. A positive delta H means it's endothermic, and that's not a good thing. So the fact that we need to override the enthalpy and make entropy the winner means we need a very high temperature. So that's the temperature that would allow the reaction to occur spontaneously. All right, guys, that's going to wrap up the last set of notes for Unit 9 and conclude thermodynamics as a whole. The next unit we're going to look at is Unit 10, where we're going to study kinetics. We'll see you there.